we're officially starting sort of the next experiment, and that is about titrations. Um, so here, doing titrations, we've obviously in lecture been talking about titrations and stuff. You just took a quiz on it, so hopefully, and there we go. So this again will be a module experiment. So you do want to make sure that you, again, follow what is in the module, not what's in the lab manual or anything like that. So when we're done talking here, obviously the module will appear up there. And again, it'll have everything that you need sort of to follow within the module itself. So again, make sure that you obviously follow what's in there. So in this experiment, we're going to talk about obviously titrations, and you're actually going to do some titrations here. And we talked in class about really 3 different types of titrations. We talked about a titration of a strong acid with a strong base. And again, in this titration, the arrangement is we have our strong base up in the burette, and we're adding to our strong acid that's in a beaker or a flask or whatever it may be. And remember that when we do this type of titration, and we actually follow the pH from kind of beginning to end there, we basically construct a titration curve. And the titration curve in this case would be a pH over there, volume of base added down here. And this would give us that kind of classic, what we talked about, S-type shape, for a titration curve. And right about there, perhaps, is our equivalence point. And remember, a couple of things about this particular type of titration are pretty much all the titrations that we sort of talked about in lecture as well, is really when we kind of developed this whole titration curve, there's really kind of 4 different spots along the way on the titration curve. And, there's sort of the initial kind of beginning. Then there's sort of like when you start adding to before you get to the equivalence point, kind of like the number 2 spot there before the equivalence point. Then obviously the 3rd spot, which is a really important spot, obviously is the equivalence point, right? So that's like your 3rd sort of important spot, and that's right at the equivalence point. And in a normal titration, what I mean was like maybe something that you would have done in, say, Chem 50, or before that even maybe, when we do a titration, we oftentimes will kind of stop right there, right? And that's sort of the point where we typically want to stop our titration, is at that equivalence point. Remember that at that equivalence point, that's the point where the moles of the acid will equal the moles of the base. So usually when we sort of do a titration, not necessarily making a titration curve like we're going to do in this experiment, but just kind of do a regular titration in the goal of finding something like, the molarity of an unknown, that's usually the point where we would want to stop. Because basically at that point, kind of the reaction is technically over in that sense. We got equal amounts of moles of acid and base. So again, a very important part. If we were not perhaps following the pH with like a pH meter or something like that to follow the pH throughout the titration curve, this is obviously where we would want to take advantage of an indicator, right? And as we talked about, indicators work over a specific pH range. So for example, phenolphthalein is 8.3 to like 10-ish. And again, at 8.3, really kind of colorless. And when you get sort of in this basic range of our indicator, it's very pink in color in terms of something it's, and again, this is obviously specific for phenolphthalein. And, we use these indicators as a visual representation, right, of we should kind of stop our titration. And that's why when we would want to choose one, we would want to choose one, obviously, there's some type of distinct color change that occurs as we approach the equivalence point. So in this type of experiment, though, and sort of what we're going to do in this experiment is we're not necessarily going to rely solely on an indicator to indicate sort of where we're at and stuff like that. We're going to kind of follow the pH using, something like a pH meter. So you could continuously sort of follow the pH as you're adding base in this type of titration. When we go kind of past the equivalence point, usually in a normal titration, it's kind of a bad thing, right? We usually don't want to continue past the equivalence point, but actually in this case, we actually do, because that will allow us to get really the complete curve, right? The complete titration curve. And that's that sort of fourth point on all these titration curves, which is when you have after the equivalence point. Now, when we look at this type of titration, like a strong acid and a strong base, like we talked about in lecture, we will produce water and sodium chloride. And remember that in this type of titration, at the very beginning of the titration, initially here, we really only have a strong acid, which means, as we talked about, really initially, you could go right into your pH equation, right? Minus the log of the H plus. Again, we haven't added anything, so we don't have to worry about, moles or anything like that. We could go right into it. It's really once you start the titration, kind of in this part, that you've obviously now started adding some of our, say, sodium hydroxide in this example. So we're adding. And that requires you, right, to do an ice table, as we talked about. And the purpose of the ice table in this particular case is we are definitely before the equivalence point, which means this is what we're starting with. This is what we're adding. And as we talked about in lecture, if we're before the equivalence point, the sodium hydroxide really will be the limiting reagent at this point and get used up completely. The hydrochloric acid will be like the excess reagent in this case. So we would do an ice table at that point. And again, the purpose of the ice table would be to figure out what is the new concentration, right, of your HCl in this case, or your strong acid, I guess is a better way to do it more generically. The importance, though, is this table does need to be in moles, right? And that's because as we add volume, as we talked about many times, the molarity changes, but the moles does not. So remember that when we're doing titration problems, we want to make sure that we do the first table in moles, and then you should convert it back to molarity at the end of like that first ice table, and obviously do whatever you need to do with that number. That then brings us to kind of the third part in this type of titration. And in this type of titration at that third point, at the equivalence point, that again is where these two guys equal each other, which means when we reach that point, both of these guys are gone. And really the only thing that we have left at that point is a salt, right? And that salt came from a strong acid and strong base. So as from our many conversations at that point, we basically know this is going to be a neutral salt, which means we would expect, obviously, the equivalence point here to have a pH of 7 in this type of titration. Clearly, if we kind of sail past the equivalence point in that fourth part of the titration, in this particular case, we obviously are now just really dumping a bunch of strong base in there, right? Because we've already at this point used up all of our acid. So we continuously sort of dump a strong base in there. And that's why we do see that pH really start to rise here, right? And that's why we also see that kind of jump in the equivalence point as we kind of get there. And then after it, it kind of continues to rise. And that's because, again, really, as we go past the equivalence point, we have now just kind of used up our acid. So we're just dumping base and we're just dumping hydroxide in there. And then now we should start to see the pH increase a lot at some point. So what do we do to figure out the sort of pH at that point in the titration? As we also talked about in lecture, at this point, you would still need to do an ice table. And the purpose of this ice table, though, would be to figure out how much of your strong base should be there at that point. Remember, past the equivalence point, the acid is gone. and that would leave you just a strong base. What ends up happening is it kind of switches around in this example. Past the equivalence point, the acid actually becomes a limiting reagent, and the sodium hydroxide in that example would become the excess reagent. That would allow you obviously to get the POH and then into the pH at that point. We also talked about a lot, right, that, you know, we do see this really vertical sort of rise as we go towards the equivalence point. And if you're being very careful upon your addition of your base as you're doing your titration, as we also talked about, you know, even by adding just that one drop, as we sort of use as an example, you know, you may find yourself, you know, over here in terms of pH, which is much higher than maybe where the true equivalence point is, which is over here. And you will see perhaps a much darker color happen on your indicator. But if you kind of look just volume wise, because we really do go vertical, they're essentially near each other in terms of sort of that equivalence point volume, which is oftentimes very important. And, you know, if you just miss it by one drop or two drops, overall, your titration is probably still okay. But if you're not being very careful and you're adding a lot of base and not really paying attention, you could find yourself with that really dark color, but have added way too much and be actually over here, which obviously would be a big difference in terms of where the equivalence point volume is. So that's why we usually, for example, most people have experience using phenolphthalein as the indicator. And that's why in most cases, they often tell you to make sure you get that lightest sort of color of pink, because that should kind of keep you within this equivalence point range. Even if you technically go past the equivalence point, you'll still be able to sort of figure that out. Any questions on that there?
So,
Yeah,
oh, I have a question, a
yeah.
quick question. So for after we reach the equivalence point, you said that we essentially run out of acid and we're left with NaOH. So because of that, we're going to use POH to find the pH.
You would. So I'm going to just get a clean page to kind of run on. So if we were sort of talking about this example here that we saw, when you would do your sort of ice table at this point, and if you're past the equivalence point, um, again, initially we'll just say we started with 4 moles of this guy, kind of like what we did in our examples in lecture. If we were past the equivalence point, we would have more moles of this guy, which means, again, this becomes kind of the limiting reagent, which means we're going to use up all of that. What we'll be really left with is 2 moles of this guy, which you can convert back to molarity. But really at that point in the solution, you pretty much have just sodium hydroxide. And if you continue to titrate, you're basically just dropping in hydroxide. Really all the sort of H plus that was there from the original acid is pretty much used up. It's all over here really at that point. And that's why at this point, the major thing that you have in that solution is this strong base. And because it's a strong base, that's really the hydroxide concentration, right? So you can't go directly from the hydroxide concentration into the pH equation. You got to first calculate that POH first and then do your subtraction of 14, right, from the POH will get you your pH. So yeah, so because of that, because you essentially have used up all the acid at that point, it becomes like a delimiting reagent and it's sort of completely gone. So really the only, besides the water and the salt that's neutral as well, really the major thing that you have that's going to affect the pH is that strong base. So that's why you would have to go POH first and then to the pH.
Okay, thank you.
Other questions on that? Okay, so when we do a titration like this, and there's a normal sort of titration, right? We sometimes know, obviously, say the molarity of, we'll use the sodium hydroxide as an example. We know, say, the molarity of the sodium hydroxide. We know, you know, how much volume it took to get to the equivalence point, right? And maybe we don't know the molarity of like the hydrochloric acid or something like that. But we know we started with like 25 milliliters of it in this titration. So by knowing the volume to reach the equivalence point, we could basically do stoichiometry, right? To back calculate and figure out the concentration of an unknown acid, for example. So in this particular example, what we would do is we would convert our 0.025 liters, which is our 25 milliliters, we would times it by the molarity of our base in my made up example here. Right, those liters would cancel. That would get you 0.5 times 0.025. I actually put the right number, 0.5 times 0.025. That would get you 0.0125 moles of sodium hydroxide. We would then do a stoichiometry between these two, right, which is a 1-to-1 relationship in this particular case. And we would know that 1 mole of sodium hydroxide gives us 1 mole of HCl, which means the moles of HCl would be 0.0125 moles of HCl. I now have the moles and I have the volume of HCl that I use in the titration. That will allow me to calculate the molarity of my HCl by taking my moles of HCl, dividing it by my volume converted into liters, which happens to be the same there. That's going to give me 0.5 molar in this case sodium 0.5 molar hydrochloric acid as the concentration. So that sort of solution stoichiometry calculation is a very common, right, calculation that we do when we are doing titrations, right? So that's oftentimes sort of the goal of a titration is to figure out, sort of what is the molarity of like an unknown acid, maybe even an unknown base if you sort of flip it around. Questions on that calculation. So that's again something that you probably have done in the past when you've dealt with titrations, maybe in Chem 50 and stuff like that, to figure out sort of the concentration. We use the equivalence point volume, and we use the molarity of the sodium hydroxide, which we know, to basically figure out how many moles of sodium hydroxide. And again, using stoichiometry from the balance equation allows us to figure out the moles of the HCl, and then obviously the molarity because we know the volume. Question on that calculation there. All right, so that was one type of titration. Obviously, we talked about a couple of other ones as well. We talked about a weak acid, strong base titration. And same deal on this, kind of the setup is our base up in the burette. Adding to our beaker or flask is our weak acid. And again, we get a similar sort of titration curve that it looks like. Also has really those same 4 spots. Our initial spot, our, kind of before the equivalence point, at the equivalence point, and after the equivalence point. But different in this type of titration, as we talked about, is since we are using a weak acid instead of a strong acid, when we do take a weak acid, say something like HF, for example, plus some sodium hydroxide, make some sodium fluoride and some water here. In this particular case, we get a couple of things that occur. First off, because at number 1, we're actually starting with a weak acid versus a strong acid, it requires a little bit more work in terms of getting into the pH. It is a Ka problem, which means you got to do an ice table with molarity, right, to get to your pH at that point. Again, you would solve for X. X would be your H plus concentration, and that would get you to your pH. Once we start the titration in this kind of second part before the equivalence point, we do need to do an ice table in moles. And as you remember, perhaps, what we end up with at that point after we do our ice table is we have a guy here, we have a guy here. Those two guys are related to each other. that pretty much makes a buffer at that point. And obviously, because you have a buffer that's left over at that point, you can go into the Henderson-Hasselbalch equation and obviously get the pH because of that. Also different when we get to the equivalence point, although it is still the moles of acid equals the moles of base. And same thing happens here as before. All this is gone, all this is gone. We are left with just a salt as before. The difference, though, is because that salt comes from a weak acid, it will go through hydrolysis, right? And we would expect a hydrolysis reaction to occur. In this particular example, we would get F minus plus some water going to make HF and OH minus. Again, here we see hydroxide being produced, as we talked about. And that's why we know that typically speaking, when we do this type of titration, we would expect a basic pH here at the equivalence point, again, because we have that salt that's going through hydrolysis that's going to basically cause that. That, if you remember, does require basically 2 ice tables. One ice table to figure out the concentration of the salt. The second ice table is really a hydrolysis problem with water and basically solving for X. When you solve for X in this case, it will equal the hydroxide concentration. And that, again, much like we just talked about a second ago, will allow you to go from POH to the pH. So again, a little bit more work, obviously, than what we have in a strong acid, strong base, where the pH is going to be 7. And obviously, kind of similar to the last one, though, when we do go kind of past that point, the equivalence point, we are, again, really same situation happening. We have now used up pretty much all of our acid. And just like we were just talking about, we're still dumping in pretty much at this point just a bunch of hydroxide or base into that beaker or flask or whatever it may be. So what does that mean? It means sort of the same situation. You'll need to do an ice table. And the result of that ice table will come out just like the previous one. You pretty much will have your strong base still left over. You will still have your salt. But as we talked about in lecture, right, between, say, sodium hydroxide and, say, sodium fluoride, sodium hydroxide is a much stronger base than sodium fluoride. So the major contributor to the pH at that point would be your strong base, or sodium hydroxide in this particular example. That, again, will get you to your OH minus concentration, to your POH, and then to your pH. Any questions on any of those guys there, like we talked about? And then the last type of titration we really touched upon in lecture was really sort of the opposite of the one we just talked about. And that's when we're dealing with a strong acid and weak base titration. And this is a little bit opposite of the other ones here. We actually have our strong acid up in the burette. So we're actually adding acid to base, right? Our weak base. And because we're sort of starting with a weak base, we're actually going to start up with a high pH, right? Because we're basically starting with a base. And what we see on this one is the curve kind of goes the opposite way, very badly drawn, but we kind of come down and around in terms of pH, equivalence point somewhere here. But even though it's sort of upside down, it's really the same exact 4 spots as the previous one we just talked about. The difference is we're just dealing with some base here. So again, this would be a KB problem, right? A weak base problem where actually you would do an ice table with molarity. You would solve for X. It would be the hydroxide concentration, getting you your POH and then to your pH. Same thing going to happen in our midsection here. What will be left over will be a weak base and is conjugate acid, which again will be a buffer. The only difference is in this case, the buffer will be really basic, as you can see from where it sort of is in pH at that point. But again, you can use your Henderson-Hasselbalch equation at this point and sort of get yourself the pH. Equivalence point, identical to what's going to happen in the previous one. All the acid will be gone, all the base will be gone, but we will be left with a salt that goes through hydrolysis, that reacts with water, and the result of that reaction is actually going to produce H3O plus, which is why we expect it to be acidic at this point. Again, going to donate that H plus over to the water to produce that. And lastly, kind of similar in part number 4 here, differences since we're adding acid at this point, what we're essentially doing when we go past the equivalence point is just dropping a bunch of H plus in there, right, coming from our strong acid. So we're just littering the place with H pluses. That definitely would expect us to see a big drop in the pH, which obviously we do see here, again, coming downward as we're adding the acid to it. And because of that, you do need to do an ice table. That ice table will give you really the concentration of your strong acid. That obviously will get you to your H plus concentration and then get you to your pH at that point. Any questions on that one? Again, basically the reverse of the previous one that we did just a second ago. Okay, so hopefully this is a reminder of stuff. I hope so. So let's talk about the actual experiment here, the titration experiment, sort of what we're going to be doing. We're going to be exploring titration curves. We're mainly going to be kind of exploring these titration curves here, you know, kind of our strong acid, strong base, and our actually weak acid. Actually, we're doing strong acid, strong base, and weak acid, strong base titration curves. So the purpose of this experiment really is to construct the entire curve. So in broad sense of what you're going to be doing is for all the parts, and there's actually 3 parts. There's part 1, which I believe is the standardization of sodium hydroxide. There's part 2 where you do 2 titration curves, one I believe with HCl and sodium hydroxide, and I believe it is acetic acid there on the second one, if I'm not mistaken. I think so. So I think it's acetic acid and sodium hydroxide. So you can again create sort of these curves here. And then part 3 is going to be an unknown acid titration with, I believe, sodium hydroxide in this particular case. So basically, you're going to be doing these titrations. You'll be doing these titrations using that Chem Collective software that we've been using. So you'll use that Chem Collective software. You'll be able to really take out on your workbench there a burette. You'll be able to take out, you know, some sodium hydroxide, some HCl, some acetic acid, maybe not all at once, obviously. You'll get a pipette. You'll kind of set it up just like normal. And you'll be able to really, again, add from your burette, again, by really dragging it over like your flask or whatever it may be. And you're going to add really the sodium hydroxide slowly. And it'll give you some instructions as to sort of how much to add at a time and how much not to add, and, you know, kind of to keep you going so that, you know, you don't end up with a ton of points or take you all day to do. So it'll give you some direction as to, you know, how much you should add. But typically speaking, when we try to sort of build a titration curve, we really want to go slow. And, you know, we want to add stuff slowly. We don't want to add a lot of volume at once, because the goal is to really kind of collect yourself, you know, a lot of points along the way. And usually the more points you have, you know, maybe it jumps up. You know, the nicer your curve's going to perhaps look. Also, kind of the more points that you have, I'll be honest with you, the most important part of sort of every titration curve is really this part of it. Yeah. And actually, this kind of front part's really important. and sort of the part near the equivalence point is usually really important parts of a titration curve. We're going to talk about why that is in just a second, but it really helps you sort of determine a lot of things about your acid, for example, that you may not know. So you're going to titrate this using that Chem collective. Again, you're going to kind of go slow so you could get a nice curve so it doesn't look like, you know, you just kind of started and then all of a sudden the next point is over here, next point's over here, and it's like, you know, maybe like that, not such a curve, but more like a staircase, right? Climbing up and stuff like that. So you want to make sure that you do add, you know, relatively slowly amount. And usually when we do this, you know, we're really following the pH. So usually with the setup that we normally have, and I think they have a picture of it maybe in the lab as well. You know, we have the burette, we have a beaker, we have a pH meter sitting right in that solution at all times. We usually have like a little stir, magnetic stir with a little stir bar in there, so you don't have to do the swirling around as you're titrating. Kind of mixes it for you as you're doing it. And then obviously we add, you know, almost drop by drop, half a milliliter, very small amount at a time. We wait for the pH to sort of stabilize because it'll take a little bit of time. And again, we're looking for very small pH movements here. So as you're adding, again, you don't really want that pH to jump a lot because, again, your curve's not going to look really nice there at the end and might not be analyzed as well. But what you'll notice, and I think you'll even notice it perhaps there as you're doing it on the Chem Collective as well, is, you know, you do need to go kind of slow because as you kind of approach that equivalence point, as we talked about, there's usually a fairly good jump in pH, right, to that equivalence point, then like a jump after the equivalence point, and then it kind of levels out. So, you know, there is going to be a point along the way as you're doing it that you'll start to see, well, I'm kind of adding the same amount of volume, but I'm starting to get a much bigger change in pH. And if you do sort of notice that, like in person, if you notice that, or if you're kind of doing it on this software here and you notice it as well, what you really want to do is try to slow down. And again, you maybe want to cut down the volume you're adding even more so that you could kind of move really slowly. And it's just going to happen as you again approach that equivalence point. You know, you're going to see this kind of bigger jump in pH is going to occur. So again, you want to try to do your best to control that so that you get this really nice looking curve, obviously, and not something that doesn't look or looks like a straight line or something like that. That's not really a curve. We'll continue to add this until we go, you know, usually we go to about a pH of 12 or something like that. So we can kind of get that leveling off effect that occurs so that we do get, when we're all said and done, this really nicely completed sort of titration curve when it's all said and done, looking at it. So that's essentially the overall sort of goal of pretty much all three parts. But let's talk about sort of specifically these parts and, you know, what information we could kind of get from the actual titration curve itself. So first off, you're going to do a titration in part one. And the goal really in part one is to figure out, when we talk about standardizing the sodium hydroxide, that's really a fancy word for I need to figure out what the molarity of the sodium hydroxide is. So kind of the goal is to figure out, you know, what is the molarity of your sodium hydroxide. We're going to do a titration of Khp, potassium hydrogen phenolate. And the first thing that really should be sort of noted is Khp, although it is the abbreviation for potassium hydrogen phenolate, that's because K is potassium, H is hydrogen, and P stands for phenolate. KHP is actually not the formula of KHP. So very commonly people think KHP is the actual formula of it. KHP's formula is actually this, I believe, something like that. That's actually the formula of KHP. So remember, you know, that KHP is actually not the formula. People use it a lot. It's a salt, and when we react it with, say, something like sodium sodium hydroxide, we do get a reaction here. And, you know, if we take out sort of this part of it here, this is basically K plus, and this is phenolate or hydrogen phenolate. That's hydrogen phenolate. And it's really this part that's reacting like an acid, like a weak acid, actually. So this is sort of acting like a monoprotic acid. Monoprotic acid, right, means that it has one hydrogen to give. So the reaction that we get is this guy plus some hydroxide, which comes from the sodium hydroxide. And we produce some water and some phenolate over here. So in this experiment, the unknown is actually the sodium hydroxide. So our unknown is kind of our sodium hydroxide, which is going to be in our burette, the molarity. What we will know in this case, and I believe even in the software, KHP is a solid. So what's going to happen is you're going to know, if it's not a solid, then it's a liquid, but I think it's a solid. So you'll know how many grams of KHP you used. You then will know basically how many moles that is by using the molar mass. And what we'll know is when we kind of do our titration, we'll eventually be able to, if we do our titration curve, or you use some indicator, which I think you will use some indicator in this one, you'll know about when it turns that light pink color, right, that you've hit the equivalence point, right? And you'll know the volume to reach the equivalence point. So if I know the moles of my KHP, I then can do a mole to mole relationship over here to get the moles of my hydroxide, which is really my sodium hydroxide. By the way, it is a 1-to-1 relationship between them, which means these moles equals these moles. And now that I know the moles of sodium hydroxide needed to reach the equivalence point, and I know the volume needed to reach the equivalence point, I could obviously divide that by the liters and figure out my molarity. So in part one, part of the goal is to really actually figure out what is the molarity of your sodium hydroxide. We're going to do this by using KHP as our known standard really here. This is sort of our known solution, our known standard solution. And in this case, in part one, again, the sodium hydroxide is actually the unknown in this case. And we're going to do a titration. And I believe, if I'm not mistaken, they will have you do kind of the whole titration curve. And you'll also, again, be looking for a change in color, because I think they will have you add some indicator there on the software as well. So just like in person, you'd probably be looking for that really light pink color to tell you that you've reached sort of the equivalence point. And obviously, you would want to note that volume as well. Again, in this case, that's sort of the goal. Any questions on part one? Now, in part two of the experiment, we're also going to be doing our titration curves of our two types of titrations that we talked about. So in part two, we are going to do that strong acid, strong base titration. And again, in this case, it will be HCl, and I believe it will be sodium hydroxide. And same thing, we're going to get our kind of curve to occur, again, by adding very slowly, following the pH versus volume of base added. And again, as we talked about just a moment ago, we would envision the equivalence point should be nearing that pH of 7, right? As it is a strong acid, strong base, and we would have sort of a neutral salt that's left over at that point. Again, by looking at this curve and sort of following the pH, you'll have a pretty good understanding of trying to find where that equivalence point should be. We're going to do sort of the same thing. You could do the same type of calculation as well. Obviously, once you figure out the volume of the equivalence point, you could do some back calculations really and figure out the molarity of your acid and verify it as well. The other titration we're going to do here in part 2 is a weak acid and strong base titration, which again is going to use acetic acid, I believe here, and sodium hydroxide. Also going to generate you a similar looking curve, perhaps the pH is a little bit different though. And our equivalence point over here. So as we talked about as well, the equivalence point in this type of titration, we should expect to be basic, again, because we're having that salt that's going to go through hydrolysis occur, and it should produce hydroxide at this point, right? So we get some of that hydroxide sort of produced. So what are we going to be kind of looking for in this titration besides the titration curve? We're actually going to try to figure out a couple of things in regards to our weak acid. First, we're going to try to figure out the molarity of the weak acid. And we're going to also try to figure out a couple of things. We're going to try to figure out what is the pKa value and our, because I don't remember off the top of my head, Ka value. So either the Ka value or the pKa value from the titration curve. So let's talk about first off how we could get the molarity. Obviously, we should expect the equivalence point, right, to be pretty vertical. So if you have this really nice curve, as we talked about before, even if you maybe can't figure out exactly where the equivalence point is, it's maybe here, you know, you're not sure if it's there or there. As we talked about, the nice thing about that is, you know, it is pretty vertical, which means even if you're off a little bit, the volume that you would get for being near the equivalence point volume is pretty much going to be the same, which will allow you to, again, to do a stoichiometry calculation, back calculate and figure out what the molarity perhaps of your acid would be. But how can we figure out the pKa or Ka value? And that's where a couple of really important points on these graphs really do come into play. And the first important point is, I'm gonna get rid of some of those lines there, or the whole curve. Let me get rid of the whole curve. That works. Try to draw it like I did. I'll go that way. There you go. All right. So one really important point is obviously we're going to want to try to figure out, you know, what is the volume of my equivalence point. So let's just say, for example, that you did this and you said the volume was 10 milliliters to reach the equivalence point. The next really important volume is actually something that is referred to as the pH at half the volume to the equivalence point. That's a lot of words to basically say my equivalence point volume is 10 in my example. Half of 10 is 5. So I would come over here to 5 milliliters. And if I technically old school it and go up to my curve and then go over to the pH scale in a straight line situation here, that pH that I would have right at that point, the pH would equal the pKa value for my acid at that particular point. So that's why I said earlier, when you're doing titration curves, the front part of the curve is really important to have a good amount of points, just like obviously knowing where your equivalence point is. But it's because we need to go from where our equivalence point is in terms of the volume to half that volume to get to our pKa value. And you may be wondering, you know, why is that? Why is it when I hit half the volume of the equivalence point, will the pH equal the pKa value? Well, let's just look at it with some made up numbers, and hopefully it'll make it understandable as to sort of what's happening at two spots. So let's first talk about the equivalence point. So again, if we're doing an equivalence point of a weak acid and a strong base, like let's just say acetic acid, like the one you're going to use, and say sodium hydroxide. Let's talk about at the equivalence point. When we get to the equivalence point, if we did this titration, we end up with some sodium acetate and some water. Now, if we use my made up examples like I've used before, say 4 moles of acetic acid, if I was at the equivalence point, that means I should have the exact same number of moles of my sodium hydroxide. That means that the change here would be -4, -4, +4, which, as we talked about, we would expect that none of these guys would still be there once you reach the equivalence point. We would actually only have our salt left over. If I put an extra 0 there at that point. This is again why we would expect the pH to be basic at that point. Again, because that salt came from acetic acid, which is a weak acid, will go through hydrolysis. Now, let's take a look at sort of the ice table here when we're actually at half the volume to the equivalence point. And this exact same titration, we would have our acetic acid, we would have our sodium hydroxide, got our sodium acetate, and we have our water. Now, initially, if we started out with 4 moles of our acetic acid, just like we did above when we were at the equivalence point, remember at the equivalence point, we would have 4 moles of sodium hydroxide, which means if I was at half the volume to the equivalence point, basically means I'm halfway there. I would have added not 4 moles of sodium hydroxide, but I would have added 2 moles of sodium hydroxide at this point. Again, at half the volume, right? Half the volume to the equivalence point, half of 4 is 2 in my example. I would have only added 2 moles of sodium hydroxide. So let's see how that affects our table. That means that the change actually will be 2 moles here, 2 moles here, plus 2 moles here. That means when we reach equilibrium, we have 2 moles of acetic acid, none of that guy, and 2 moles of this guy. Now, if we look at what we have left at this point, at half the volume to the equivalence point, that is acetic acid and sodium acetate. That is a buffer, right? And we're in that buffer region that we talked about in this type of titration curve, which means if I wanted to calculate my pH would equal pKa plus the log of the base over the acid. That means the pH would equal the pKa plus the log, in this example, of 2 divided by 2, which means the pH is equal to pKa plus the log of 1, which means the log of 1 is 0, which means at exactly that point in this type of titration, if you get to half the volume of the equivalence point, you are now at the point where the pH will actually equal the pKa value of that weak acid. Question on that? So this is why in a titration curve, especially in a weak acid, strong base titration, or even like a strong acid, weak base titration, that sort of beginning part of your curve is really crucial. Obviously, where your equivalence point is also very crucial. But because you need to kind of go back and figure out at half that volume, what the pH is, because that will allow you to get to your pKa value of your weak acid. Any questions on that? If I have the pKa value, I could get the Ka value. It would be 10 to the caret minus pKa, inverse log of the minus pKa, will give you your Ka value. So you could kind of convert it back to a Ka value if you wanted to. Any questions on that part of it? Okay, so that's really sort of a major goal of part 2 of the experiment, maybe part 3 as well, is to use your titration curve to basically figure out what the pKa value of your weak acid is, or your Ka value as well. Now, what I sort of showed over here is sort of like, sort of the old school method here. It's how we used to do it, plot it by hand, do a little lines, go over with some rulers. Nobody wants to do that. So what you're going to do after you, again, use the Chem Collective and sort of do your titrations and your titration curves, after you do that, you're actually going to use a computer software program to analyze your titration curve. You're going to make what is sometimes referred to as a first derivative plot. And what that's going to do for you is help you determine where your equivalence point is, where maybe half your equivalence point volume is. So when you're all said and done, after you do the actual titration on the software, you make this graph. Very badly graphed there. Let's try that again. Maybe your graph will look like that. I don't know. It happens, I suppose. Maybe it's got that little. I'm not sure that's any better, but we'll go with it. So what you're going to do is you're going to have this graph, and you can actually do it by hand if you really know how to use Excel. You can make an Excel graph and do it. But there's actually a computer program that you're going to use, which is, I think it's the Vernier software, if I'm not mistaken. I think it's the Vernier software. And you're going to be able to put in there and make really a first derivative plot. And what is a first derivative plot? It will basically plot the change in sort of volume versus the change in pH on your graph. And it basically will give you a plot that, and again, I'll apologize for a really bad move right here. It's going to give you a plot where you're going to see this sort of peak occur. And where this peak occurs, which is your first derivative plot, that it should correlate to your equivalence point. I obviously missed it because I freehanded it, but it will correlate to really your equivalence point volume. So kind of where you see that really big peak occur, or the peak occur in your first derivative plot, when you use the software to analyze it, that's going to really indicate where your equivalence point is. You'll also be able to kind of move about this first derivative plot to really sort of narrow in on where the volume of the equivalence point is. And you'll be able to really narrow in, like, hey, for example, it was 10 milliliters. And then what you can do is, with that software, kind of move your cursor and go, okay, I need to move it back to like 5 milliliters. And you'll be able to move it back to about 5 milliliters, and you'll be able to get the pH at about 5 milliliters. And obviously that would get you your pKa value. So you're going to also use, again, this sort of Vernier software to sort of analyze your titration curves. It'll give you really what's referred to as a first derivative plot. And again, really wherever it peaks is basically where your slope changes a lot. So that's because right as we approach the equivalence point, it goes from jump in pH to jump in pH. So we get this vertical rise towards the equivalence point. And that's really where the slope of that line changes a lot. And that's really what this is measuring, is that kind of big change that occurs. Because up to this point, it's pretty level, right? And that's why our first derivative is pretty level. But then we get to this point where the equivalence point is, you get that really big jump. And that's what's related by that peak that we see. And then on the back end of the curve here, right, where we're really basic, it does level out again. And that's why it comes back down this curve and sort of levels out as well. So it sort of gives you this inflection point of where you get a pretty big change in that pH in this type of graph. And again, that will allow you to really hone in on the pH at the equivalence point, also give you some ability to sort of move along that kind of curve to really kind of narrow in on the volume you're looking for. Will you be able to hit the exact volume? Like, will you be able to find a point that's exactly at 5? You might not. So, you might need to maybe find the point before that, the point after that, maybe do a little averaging to sort of get you to, where you need to be. So you might be able to find the exact volume, or you might find something that's very, very close to it. So there might be a little bit of error, obviously, associated with that. Any questions on that? Okay. All right, so the third part of the experiment, kind of very similar to the second part. The only difference is you're going to really, you really will just be doing a titration of an unknown acid. And I believe, again, if I'm not mistaken, I think these unknown acids are going to be solids up on the computer program. So you'll have to weigh out some grams, I think, of it, if I'm not mistaken. And you're going to kind of set up the same thing. You're going to have your burette. You're going to have some sodium hydroxide in there. You'll have your unknown acid down here. And again, you're going to be generating your titration curve like we did in all the other parts as well. And you're going to do your analysis again with the computer program, and you're going to try to isolate where your equivalence point is. You'll try to isolate where half the volume of your equivalence point is, and try to determine where your pKa and pH equal each other and get that value. You'll also be able to perhaps figure out, actually, I think that's all you'll be able to do. I think you'll be able to figure out the molar mass. I'm sorry. You will be able to figure out the molar mass as well. So the molar mass is grams per mole. So you might be wondering, again, how do you get these numbers? So the first number is pretty simple. That's how many grams you weigh out when you do the actual titration. The moles are going to come from your titration. So you'll know the molarity of your sodium hydroxide. You'll know the volume of sodium hydroxide, obviously, to reach the equivalence point. From that will allow you to get the moles of sodium hydroxide. Once you have the moles of sodium hydroxide, you could do a mole-to-mole relationship between the sodium hydroxide and your acid, your unknown acid. And once you get the moles of that, that would be the bottom part, and you'll be able to figure out the molar mass. So you'll actually be able to figure out really two pieces of information for your unknown acid. You'll be able to figure out the pKa value, and you'll be able to figure out the molar mass. And I believe you'll be able to check the ID of how good you did on the Chem Collective software. So I believe there will be a box or something once you do sort of this analysis that you could kind of enter your values in and enter like, hey, my pK value was this and my molar mass was this. And I think it will tell you either yes or no, like you did it right or got it right or wrong. You'll need to take a screenshot of all that as well. I believe it says in the instructions, but you'll be able to sort of check yourself along the way. Any questions on part 3 there of the experiment? Now, one last thing just to remind everybody, right? If you don't know sort of what your acid is, you could always use generic sort of formulas. HA, right, is what is referred to as a monoprotic acid. And that basically means it breaks apart into H plus and A minus, right? We have diprotic acid, which would be represented by H2A. Right? This would break apart into 2 hydrogens. And the A here, the negatively charged anion, would actually have a -2 charge, right? And we have a triprotic acid where you could represent it by H3A. 3 H plus is coming off. And the A here would have a -3 charge. So, I almost think, and I could be wrong, but I believe, and it should say somewhere, I almost think that maybe the unknowns in the software, they're all monoprotic acid, which means really you'll have kind of like a 1-to-1 relationship. Remember though, if by some chance it mentions it's diprotic or it says it's diprotic, That is not going to be a 1-to-1 relationship, 1-to-2 relationship, 1-to-3 relationship. And what that would affect would be right here. Yeah. So when you got your moles of your base, if it is a monoproduct, it would be a 1-to-1 and it would be the same number. But if it's a diprotic or triprotic acid, you would have to kind of write out the balance equation to get the right mole to mole relationship. I almost think they're all monoprotic, but again, I might be mistaken on that. Any questions on that there? Okay, any questions on this experiment? That's essentially the whole sort of ball wax there. You're basically going to be kind of, again, using this program to do these simulations and titrations. You will be recording information, so you'll find some notebook pages up on the module as well, where you could record your measurements of pH and volumes along the way as you're doing your titrations. Remember as well, there's certain parts where it asks you to take a screenshot. So make sure you do take those screenshots using the software along the way. So make sure you follow sort of the instructions on that. In terms of the lab report for this one, this will be a formal lab report. So this one, we haven't typed anything in a while. So this will be a formal lab report that you do need to type a report for. And it will be a 4 with an E. There you go. We'll have an introduction, right? In this case, we will have a data section. We'll have a results and discussion. And obviously post-lab, probably some pre-lab questions. I think there are too. And I think that's about it. So this will be, again, kind of like the couple that we did before, more of a formal lab that you need to type up. We will be working